In this video, we're going to cover the second part of Unit 2 for AP Physics 1. We're going to begin by defining uniform circular motion. So when we say that, what we're talking about is an object that moves in a circle at constant speed. And when an object is moving in a circle, it has what's called a centripetal acceleration. This is the acceleration of an object moving in a circular path. And we're going to demonstrate that this acceleration is always towards the center. Now, remember that centripetal means center seeking. So when you see that term, it gives us a hint that it's towards the center. Here we have an object going in a circle. And you'll notice that the velocities are tangent to the circle. So we have v1 tangent to this point, v2 tangent to this point of the circle. And to find the change in velocity, we can take the vector v2 minus v1. v2 is in this direction. v1 is going to be, the negative v1 will be in the opposite direction that's shown here. So it's going to be going down. And the resultant vector here is delta v, which is going to be in this direction, which is towards the center. So we know that delta v is towards the center. We also know that acceleration equals the change in velocity over time, and the direction of the change in velocity is also the same as the direction of the acceleration. So if the delta v is towards the center of the circle, the centripetal acceleration will also be towards the center of the circle. Now we're going to derive an equation for centripetal acceleration. To do that, we're going to go back to our velocity vectors here, and we're going to label this angle theta. Because v1 and v2 are both perpendicular to this radial line, this angle over here will also be theta as well. I'm going to redraw this piece of the circle over here. This curved line right here is the arc length. It's just the distance of this curved line. And if theta is very small, then we can approximate this curve as a straight line. Now this arc length is equal to vt. V here is going to be the speed of the object and t is the time. And using proportions, we're going to relate this circle to this circle. So we're going to say delta v over v, so here are the two sides of this triangle here, is equal to vt, which is this shorter side of the triangle, over r, which is the longer side of the triangle. And then we can move the v's over, moving this v to the right, and then moving the t to the left. I get delta v over t is equal to v squared over r. And then if we substitute a for v delta v over t, we get that the centripetal acceleration is equal to v squared over r. Now, sometimes an object might be going faster and faster in a circle. And if that happens, not only does it have a centripetal acceleration, but it also has a tangential acceleration. And this is the rate at which an object's speed changes and is directed tangent to the object's circular path. So you can imagine like a merry-go-round where it starts to go faster and faster. It started from rest and then it's going faster and faster and faster and faster. So not only does it have a centripetal acceleration towards the center of the circle, it also has a tangential acceleration, which is tangent to the circle. And the net acceleration is the vector sum of the centripetal acceleration and the tangential acceleration. So you add the vector sums of AT and AC, that gives you the net acceleration of the object. As an object moves in a circle, one of the things we can calculate or we can measure is the period. And the period is the time to complete one revolution or rotation. And the unit for this is seconds. We can also calculate its frequency, which is the number of revolutions per second. The unit for frequency is hertz, or capital H, little z. The relationship between period and frequency is an inverse relationship. So the period is equal to, and the symbol for period is capital T. Period is equal to 1 over the frequency, or frequency is equal to 1 over the period. Now, since the speed is equal to distance over time, for a circle, we can use this equation. V, by the way, V is velocity, but here we're just talking about the magnitude of the velocity, so we're really talking about the speed here, is equal to 2 pi r. So that's the circumference, which is the distance around a circle, so 2 pi r, divided by capital T, which is the period. So using S equals d over t, we can rewrite it for an object going in a circle. To find its speed, it's just the circumference divided by the period, the time to make one complete circle. And we can rearrange it to solve for the period, which would be 2 pi r over v. In order for an object to move in a circle, there must be a centripetal force. This is the net force that causes an object to move in a circular path. So there's a lot of details here that we got to be real careful about when we talk about centripetal force. First, it is towards the center. Second is that it is not a new force. It is any force can play the role of centripetal force, like gravitational force can play the role of centripetal force, tension can play the role of centripetal force, friction or normal, etc. So we got to be real careful that centripetal force is not a new force. It is a net force, which can be played by any of these forces that we've learned previously. To derive the equation for centripetal force, we can take Newton's second law, net force equals ma, combine it with the equation for centripetal acceleration, AC equals v squared over r, and then we get that the net centripetal force equals mv squared over r. Now let's take a look at some examples where objects are moving in a circle, and let's identify what the force is that's causing that's playing the role of the centripetal force, and how we would set up an equation to solve a problem like that. So here we have a car moving in a circle. And at this point here, the centripetal force is towards the center. The force that's playing the role of centripetal force is static friction. And even though the car is moving, it's not sliding side to side. And so the static friction is playing the role of centripetal force. Now imagine if there was no static friction, then this car would skid off. As far as the equation, we would substitute the net force, net centripetal force with Fs, the static friction force, is equal to mv squared over r. Here we have a planet going around the sun, and the force playing the role of centripetal force here is gravity force, and the equation would be Fg equals mv squared over r. Here we have a barrel ride, and this is a ride at an amusement park where it spins around. And the force that's playing the role of centripetal force, ROLE, playing the role here, is this person, is the normal force pushing on this person. So the wall pushing on this person around, that force is playing the role of centripetal force. So we can set that equation as Fn equals mv squared over r. Over here, we have a ball on a string, and we're swinging this horizontally. And so we have tension force because the string is pulling on the ball, and that force is towards the center. And the equation would be Ft equals mv squared over r. Now we're going to take a look at a little bit more complicated situations. Some of these will have more than one force contributing to the centripetal force, and some of these will have components that are contributing to the centripetal force. So let's take a look at this roller coaster. So this roller coaster that's going around, at the highest point, there are two forces acting on it. There is the normal force, and then there's gravity force pushing down. And then if you were to solve this problem, we would set this equal to mv squared over r. Here we have a ball that's swung vertically at the highest point. There's gravity force pulling down, tension force pulling down. So the equation is Fg plus Ft equals mv squared over r. Here we have the ball swinging in a vertical circle at the lowest point, and notice that the Vt is greater than Fg, and that's because the centripetal force, the net centripetal force, needs to be towards the center, so we know Ft has to be greater than Fg. So the equation here is going to be Ft minus Fg equals mv squared over r. We're going to take the force towards the center minus the force away from the center. That's how you figure out how to write down the net force on the left-hand side. Here we have a car going through a dip, and the center of curvature of this dip here is going to be above the car. So the normal force has to be greater than the gravitational force. So we're going to write Fn minus Fg equals mv squared over r. Once again, for the net force, we're going to take the force towards the center minus the force away from the center equals to mv squared over r. Here we have a car going over a hill. There's a gravitational force down, normal force up. The center of curvature of this hill is below, it's going to be down, so Fg has to be bigger than Fn. So our equation will be Fg minus Fn equals to mv squared over r. Now here we have a conical pendulum, so we have a ball on a string that's going in a circle. Some classes will do the flying pig experiment or lab, and the flying pig is going in a circle. And in either case, the centripetal force here is played by a component of the tension force. So this tension force is in this direction at this angle, and the horizontal component of the tension force, which is towards the center of this circular path, is Ft cosine theta. because it's a side next to the theta. So ft cosine theta for the equation that we would set up for this problem would be ft cosine theta equals to mv squared over r. Now we're going to take a look at another roller coaster problem, but here's the question, which is what is the minimum speed that the roller coaster needs to make it all the way around? When a roller coaster goes around a loop here, there's gravitational force and there's some normal force. To find the minimum speed to get all the way around, we're going to set the normal force to 0. So this means that it's barely going to get around. And if we set the normal speed to 0, Fg is mg, right? Mg equals to mv squared over r, centripetal force equation. And then if we cancel out the m's, we get v is equal to square root gr. So the square root of gr will give you the minimum speed to make it all the way around the loop. Of course, you can go faster. If you go faster, you're going to have a greater normal force. But if you set the normal force to 0, that's the minimum speed you need to get around the loop. Next, we have a car going around a banked turn. There's gravitational force down. The normal force is perpendicular to the ramp. The centripetal force here is going to be the horizontal component of the normal force. Now, how do I figure out these angles here? So we're just going to use geometry here. So if you take a look at this ramp here, we have theta, right? And if you extend this line all the way through, these two angles are alternate interior angles. So I know these two angles are the same. Now, this forms a right triangle. I'm going to call this alpha. So alpha and theta are complementary angles. They form 90 degrees. They add up to 90 degrees. This is a triangle and right triangle. So I know this angle and this alpha has to also equal 90 degrees. So this also has to be theta. So I know this is theta, and so the horizontal component of Fn is going to be Fn sine theta. So if you're working on this problem, you would substitute for the net centripetal force. You would write Fn sine theta equals to mv squared over r. Now we're going to take a look at Newton's law of universal gravitation, which tells us that all masses attract each other with a gravitational force. Now this force is always attractive, and the two forces are going to always be equal and opposite direction. So this reminds us of Newton's third law. And it doesn't matter if one object is bigger than the other. The forces will always be equal in an opposite direction. And I'm using this dotted line right here just to indicate that these are Newton's third law force pairs. These are force pairs. These are action-reaction forces. The equation for Newton's law of universal gravitation is Fg equal to big G m1 m2 divided by r squared. M is the mass of the object. Big G is the gravitational constant, 6.67 times 10 to the negative 11 Newton meter squared divided by kilogram squared. So this is called a constant because it's the same anywhere in the universe. It doesn't depend on location. And then r is the distance between the centers of the two objects. So if you're dealing with large objects, we're measuring from the center to the center of the two objects. Gravitational field is the space of gravitational influence. And there are two ways to measure the gravitational field. One is to place a test object in the field. So for example, you could have an apple. You measure the weight of the apple divided by the mass of the apple. That will give you the gravitational field at that location. Another way to measure gravitational field is to use the mass of the object, the large object that is generating the gravitational field. And we can derive this equation by substituting Newton's law of universal gravitation for Fg. So remember, Fg is big G times m1, m2 divided by r squared. Notice that the little m's cancel out, and that leaves us with little g is equal to big G times big M divided by r squared. Big G is the gravitational constant. Big M is the large mass generating the gravitational field. So usually this would be like a planet. It could be the moon. It could be the sun. But generally it's a large mass. And R is going to be the distance from the center of that large mass to the location that you're measuring the gravitational field. Since we can't directly see gravitational fields, one of the ways we can visualize it is to use what are called gravitational field lines. And here you can imagine a large planet, and we have lines. These lines are representing gravitational fields, and we call these lines gravitational field lines. Where the lines are closer, such as over here, we have a stronger gravitational field. Where the lines are further apart, we have weaker gravitational fields. So this is just a way for us to visualize the gravitational field, where it's stronger, where it's weaker. The direction of the gravitational field points towards the direction that a mass in the field would get pushed. So if I put an apple over here, it would get pushed in this direction, and so the direction of the gravitational field here is going to be in that direction. Now, this is a graph that shows you as you're moving away from the Earth. So here's the surface of the Earth right here, and this tells you the gravitational field at the surface. So on Earth it would be 9.8 newtons per kilogram, and then as you're moving away you can see that it decreases, and you can see that it's an inverse relationship. It's actually an inverse squared relationship. The gravitational field near a planet is numerically equal to the free fall acceleration. So when we talk about gravitational field, we say that it's 9.8 newtons per kilogram. It tells us how much force, gravitational force, is pulling on the object for every kilogram that it has. The acceleration due to gravity is also 9.8 meters per second squared. Now, numerically, these two are the same. And unit-wise, you could see that they are equivalent because newtons over kilogram is equal to, and we know that newtons is a kilogram meter per second squared. Newton is a derived unit, which is equal to kilogram meter per second squared. And the kilogram, you can see that they cancel out, so which leaves us with meters per second squared. So these units are also equal to each other. Now we're going to compare inertial mass and gravitational mass. Inertial mass measures the object's resistance to changes in motion when a force is applied. So if we exert a force on this green mass and measure its acceleration, we can calculate the inertial mass by taking the force divided by the acceleration. For gravitational mass, this determines how strongly an object interacts with a gravitational field. So on Earth, we know that the gravitational field is 9.8 newtons per kilogram. And if we weigh this green mass here and get its Fg, we can take the Fg divided by the gravitational field, and that would give us the gravitational mass. We could also do an experiment like the Cavendish experiment, and using this, we can measure the gravitational force between the spheres. We know the gravitational constant, and if we know one of the masses, either the green or the yellow spheres, and we know the distance between the spheres, we can calculate the mass of the other sphere, and that mass would be its gravitational mass. Now, experimentally, the inertial mass and the gravitational mass are always found to be numerically equivalent. So although we have different ways of measuring these masses, the number associated with these masses are always the same. For both Newton's law of universal gravitation and the gravitational field equation, you'll notice that there's an inverse square relationship. And so we can say that the gravitational force is proportional to 1 over r squared, or you can say that the gravitational field is proportional to 1 over r squared. And so I want to take a moment to talk about the inverse square law. So if the r doubles, the Fg will change by a factor of not 1 over 2, so that's a common mistake. You'll notice there's a square there. It's going to be 1 over 4. Okay. If the r is halved, so if this bottom part is halved, right, we need to flip that, right, because it's in a denominator. So it's going to change by a factor, not 2. So that would be a common mistake. So we think half, reciprocal of half is 2 over 1, but we need to square that. So it's going to change by a factor of 4. Next, we're going to derive orbital speed and period. Now, this is really cool because here we're going to combine our understanding of centripetal force equation and Newton's law of universal gravitation. So when an object is going around the planet, let's say we have a moon that's orbiting the planet, we can set the net force. The net centripetal force here is going to be a gravitational force. And the gravitational force, we could use Newton's law of universal gravitation, big G, m1 times m2 divided by r squared. So we set that equal to mv squared over r. The m's will cancel, and one of the r's will cancel, and that gives us big G, big M over r is equal to v squared. Now be real careful that this big M is the central mass. In this case, the central or the large mass is the planet. And if we solve for v, we get v is equal to square root big G times big M divided by r. This gives us the orbital speed. So this is the speed you would need to stay in a circular path. Of course, if you go faster, then you're going to go in an elliptical path. If you go slower, you also go in an elliptical path. If you go too slow, you're going to crash into the planet. Now, we know that the speed of an object going in a circle is the circumference divided by the period. And if we plug this into v, and I'm plugging that into v here on the right-hand side, and we square it because this v is squared, we get 4 pi squared r squared over t squared. And if we solve for t, we get this equation, t squared, this is the period squared, is equal to 4 pi squared over big G over times big M times r cubed. And so you'll notice that the period squared is proportional to the radius cubed. This is the radius of the orbit, and this is Kepler's third law. Now we're going to use Kepler's third law to answer a experimental design question, one that you might see on an AP Physics 1 exam. So you might be given some data, which include the period of an object going around, maybe the moon going around a planet, and then also the radius of the orbit of the moon going around the planet. And they're asking you to calculate what is the mass of the planet. So if you graph the period squared versus the radius cubed, you get a slope, and that slope is going to represent this value right here, 4 pi squared over big G times big M. And how do I know that? Because this has the format of y equals mx plus b, the slope-intercept equation. And the slope right here, the m right here, is the 4 pi squared over big G times big M. When you are calculating the slope, we want to be very careful that we don't just use data points. We want to make sure we use points that are on the best fit line. So the yellow right here are your data points that you got from the exam question. And then so you draw your best fit line, which is a straight line that's as close to as many dots as possible, but it is not connecting the dots. And then you're going to pick 2 points, and here I picked these 2 blue points. These 2 points are the ones I'm going to use to calculate the slope. So the slope equation is y2 minus y1 divided by x2 minus x1. You could also use rise over run as well. And then we know that the slope is 4 pi squared over big G times big M. And so setting the slope number that I got, I'm going to substitute that for the slope. I'm going to solve for M. So I'm going to isolate the M, substitute the slope number here, and solving for M, that will give us the mass of the planet.